Okay, so this question, we need to explain in a few words, why do we see the colourful spectrum on a soap bubble in reflected light? Why do different colours appear under a different angle of observation? And we can use sketches showing two different angles for our explanation. Cool. So for this question, let's start off by drawing our thin film of soap, for example, on top of water. So this is going to be soap. We can assume that this is air and this is going to be water under here. Now, I'll put NS, NA, NW. So we can say that, firstly, that the index of refraction for soap is going to be greater than that of water, and that's going to be greater than that of air. So that's going to mean that, remember, for a soap bubble, as we have rays coming in, that we're not going to get a phase change off the reflection off the back of the soap film. Okay, cool. So we have a ray coming in like this. This angle, this is our incident ray. This angle here is going to be theta. Now, what's going to happen when the ray travels through the soap is that it's going to travel slower. Therefore, it's going to bend towards the normal. So this is going to be our angle of refraction in here. And then what we have is from the surface, we have a reflected ray, which is going to be R1. And this angle in here is also going to be theta. And then we end up with a reflection at the bottom, and then we end up with a ray R2 that has gone through. Okay, so the thickness of our soap film is going to be L. Okay, so what we can say for starters is for small angles of theta, so for small incident angles, what we can say is that the path difference between the two rays is going to be approximately equal to 2L. Now, the actual path difference, remember, is going to be 2L, but there's also angles and everything in here as well. So we can say, though, that it is approximately 2L. And remember, we have a wavelength of light. The wavelength of light in the soap is going to be theta divided by NS, where theta is the wavelength of light in air. So this is just showing that, remember, there's a change in wavelength when we go to a different material. Okay, so because there is a reflection here, R1 has had a phase shift of half a wavelength, remember? It's had a phase shift of pi because it has reflected off a surface with a higher refractive index. Therefore, then, for constructive interference, we need to take into account not only the fact that there is a path difference, but also the fact that we've had a phase change. So therefore, constructive interference is going to occur when we have a path length difference that is equal to m plus a half lambda. That's lambda ns, which is going to be m plus a half lambda divided by ns. And m in this case is 0, 1, 2, etc. So that's for constructive interference. And therefore for destructive, our path length difference is going to be equal to m lambda ns, or m lambda divided by ns. And m in this case is 0, 1, 2, etc. Excellent. So we see a colourful spectrum on a soap bubble because, remember, these are all interfering in different, not only are these interfering in different ways, because it's all coming in at a different angle. What's also happening is that we have different angles of refraction. So what happens is when white light comes in, the colors are all going to refract a different amount and it's going to spread it out. This is also dependent upon the angle of incidence. That's how you do this question.